Hello, pre-calculus students. I'm going to talk to you about log functions, and not the kind where you end up chopping wood. Logs came about because multiplication can be pretty tricky. But if you have multiplication of numbers that are base with an exponent, and the bases are the same, you can just add the exponents, and there's your multiplication done with addition. So this is 9 times 81. Yeah. And it ends up being 3 to the 6th power, which is 729, I believe. We can check it. 3 raised to the 6th power, 9 times 81. Same answer. But with the 1, I just added the exponents. Let's try 4. 4 squared is 16. And 4 to the 3rd power is 64. So if I wanted to multiply 16 times 64, it will give me, since the bases are the same, I just add the exponents. 2 plus 3 is 5. 4 raised to the 5th power, 1024. 16 times 64, 1024. Okay. Now this is the one I wanted to really talk to you about. 10 raised to the 2.3 times 10 raised to the 3.1 equals 10 raised to the 5.4. What in the world? Why would you even care about this? Well, like I said, addition is easier than multiplication. And since we have a base 10 numerical system, you could use this thing called a slide rule and change any number to a base 10. Any number. So let me show you. 365 times 999. Using your slide rule, you could change it to 10 raised to the 2.562. Oh, I left that as a 5 instead of a 6. Hang on. Okay, there. I switched the, it ended up like being 5, 6. So I rounded to 6, but I forgot to write it on here. So, changing to exponents, adding the exponents, and then using your slide rule again will give you a pretty good approximation. Now, I had some real big rounding here, and so the actual number is 364,000, which was fine, but the last 3 digits were off by about 200. Let me show you. 365 times 999. See, we got the 364,000, and then I was off by about 200. That was a pretty big rounding error. We don't have slide rules. So how in the world did I get these numbers? Well, I used a log function, because a log function tells me what the exponent is. Just like 10 squared is 100. Well, the log of 100 is, come on, enter, is 2, because log is interested in base 10. 10 raised to the 2nd power is 100. So when I was looking at 365, I didn't know what 10 raised to whatever power. I knew it was between 2 and 3, because 2 is 100 and 3 is 1,000. See, 10 raised to the 3rd power is 1,000, but I don't know what 365 is. So I said log 365, enter. And you can see that I had some severe rounding error because I just stopped right here. 562, chop the rest of it off. And then 900, whoops, clear. Sorry, log of 999 is something that's really close to 3, you notice, because 999 is really close to 1,000. And I actually went out an extra decimal because of the rounding, because if I started rounding here, I just have 3, and that's not quite what I was looking for. So you can see that's where I got 10 raised to the 2.56 and 10 to the 2.9996, and then I added it together and got kind of close. 10 raised to the 5.5616, and you can see I chopped off the decimals because I knew I wasn't going to have this anything after the ones. So slide rules became really useful with exponents. And then we started saying, oh man, well, we can have different bases besides 10. If we have base 2, now we're talking computer language. Because 2 raised to the 6, okay, it's hard to explain because I have to change that to base 2 numbers right there, and that's it's really hard to do as far as I can think of. But we can have a base 3, we can have a base 4, we can have a base 100. But because the 10 was our numerical base, originally log functions were all base 10, and that's why we have a log function. And if you can narrow in, you see there's a 10 raised to the x above it. That's because 10 was so popular. Now, right below it is something called ln, natural log. And above it is an e to the x. If you get into calculus, you will find that e to the x is very popular. Now, when I taught pre-calculus before, I could spend more time on the money. I got told I was spending too much time on interest rate, and the student loan activity I gave you was as close as I'm allowed to get. But let me show you a website. Okay, the calculator site, whoa, can do the unit conversion and all that. But it has this really nice formula right here, that the amount, remember we're talking the total amount that you paid on your student loan depended on how much you took out, what the interest rate was, how long you were going to have the loan for, and then number of times interest is compounded. Now if you've got a credit card, you know this is probably monthly. Student loan, monthly. Car loan, monthly. And all these things I could put into a calculator. You use an interest calculator when you're doing the activity, but this is the formula it's coming from. And people found that as you compounded more often, instead of monthly, what was weekly or daily or every hour or every minute or every microsecond, this number here changed to something called E. It's just a number, but it started approaching, taking a limit towards E, raised to the interest rate times the time. And that became, that's how I like to talk about it when I bring up E. this number's been known for a long time. It's like pi. Pi was from ancient Greek. E has been known a little sooner. It's called a natural number. It's 2.7 blah blah blah. You don't need to memorize it. Just like pi, you don't need to memorize pi. It's one of those repeating number. Not repeating. It doesn't repeat. It's an irrational number. And it's given the abbreviation E because the first person that really talked about it was named Euler, and his name started with an E. So, E raised to a power is also something that we talk about a lot. And it's just as powerful as log, but because E is the natural number, the log of base E is called the natural log. So on your calculator, see, clear this, clear. So second, see how E is attached to natural log? If I just raise it to the first power, you can see that E is 2.71828, blah, 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 blah. Just like pi, right here, is just a number. 3.141592, blah, blah, blah. Okay. They're just numbers. They're irrational numbers, but they are pretty powerful. And so, 56 can either be changed with log, or it can be changed with natural log. They are not the same. So, the log of 56 is a number between 1 and 2, because we're trying to raise 10, and it's going to be between 10 and 100. So this is 10 raised to the 1.7482. A little bit higher. So you can see 56 point, and then we've got decimals. Now, if I did the natural log of 56, I've got 4. So I told you they were not the same. E is a number between 2 and 3, and 2 raised to the 4th power is 2, 4, 8, 16. 3 raised to the 4th power is 81. So it's a number between, you can see that 56 is between 16 and 81. So E, second E, raised to the 4.0253. Okay, this is going to be a number a little bit less because I'm chopping off. Enter. But it's pretty close to 56, isn't it? So, log functions basically say, you tell me the base, I'll tell you what exponent you need to have to get the answer. Let me pause. Okay. When we're looking with any sort of base, we say log base b of a for answer equals a constant. That's an exponent. Now I couldn't put in e for exponent because e is taken. We can't use that. But when we do, we can sort of undo it. Well, I've got less than a minute left. Insert an equation. I don't know where the equation went. Try it again. Insert an equation. Right beneath my picture. There we go. We say b raised to the exponent equals a. I'll make that bigger so you can see it. Come on. Then I'll have to do another slide, but bigger, 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 bigger. These two are considered like inverse functions of each other. Base raised to the exponent, answer. Log base b of answer is C.